Welcome to this deep dive. Today, we're looking at something you've likely seen, maybe, without giving it much thought. Mini sand dunes.
Yeah, those little ripples, the kind you see on a beach, maybe, or even in gravelly spots.
Exactly those. They seem simple, but how they form has actually been a bit tricky to explain.
That's right. The science that works for, huge desert dunes, like in the Sahara, it doesn't quite line up for these tiny ones. It's been, well, a puzzle.
So our mission today is to unpack some new research that seems to crack this puzzle. We'll look at how these mini dunes get started, and then, interestingly, how that might connect to places like Mars.
This is all based on a study in PNAS, led by the University of Southampton, working with quite a few international institutes. And it really does offer a fresh perspective on how sand moves around.
Okay, let's set up the puzzle first. Big dunes, the classic picture is, well, wind moving lots and lots of soft, dry sand, right?
Yeah.
Grains rolling and bouncing along close to the ground.
Exactly. And that model works great when you have, endless supplies of that loose, dry sand. Loads of it.
But that theory sort of hinges on having that perfect, soft, sandy surface everywhere.
It does. And that's the problem. These mini dunes, they often form where you don't have that.
Right, like on a beach where the sand might be damp, a bit sticky, or on harder ground like gravel.
Precisely. Scientists call them small-scale sand bed forms. They're tiny, maybe just a few centimeters high. The paper mentions up to about 6 centimeters. And they show up in places where sand doesn't just easily roll.
And another thing is how fast they appear, isn't it?
Oh, incredibly fast. The researchers actually clocked them forming, growing to their full, albeit small, height, that 6 centimeters or so, in maybe just 30 minutes.
30 minutes, wow.
Yeah, and they can vanish just as quickly. Wind changes, tide comes in, poof, gone.
Yeah.
Which, makes them really hard to study in detail, their speed, their size, stuff.
So the old theory needs lots of soft sand and explains slow growth. Mini dunes form fast on wet or hard surfaces. That's the mismatch.
That's the core of the problem, yeah. So this team from Southampton, Paris, Oxford, Loughborough, Illinois, Denver, quite a group. They tackled it differently.
How so?
They used high-resolution laser scanning out in the Namibian desert.
Yeah.
Basically getting super detailed 3D snapshots of these things forming, moment by moment, plus lots of field work.
Laser scanning in the desert. That must give you a whole new level of detail.
It really did. And the key thing they saw, the crucial bit, was about how sand grains move on these harder, more, let's say, consolidated surfaces. Instead of just rolling or doing little hops near the ground, like on soft sand, they bounce higher.
Higher? Like how high?
Significantly higher, maybe up to a meter or around that off the surface. The wind catches them more easily in that higher trajectory.
Wait, a single grain of sand bouncing a meter high? That feels completely different.
It is. It fundamentally changes how you think about the sand transport in these environments. And that's the basis for their new explanation.
So how does that higher bounce lead to a mini dune?
Well, imagine these high-bouncing grains being carried by the wind. When they eventually come down and land on a patch that's maybe a little softer, could be just a tiny depression, or an existing ripple, they don't bounce off again as easily. They start to accumulate.
Okay. So the bouncier grains find a spot where they can actually stick the landing, so to speak.
Exactly. And that first little pileup, maybe just a few grains thick, that's your proto-dune, the seed.
And then?
Well, even a tiny bump changes things. It disrupts the airflow right at the surface, just slightly.
Like a miniature version of how a big dune shakes the wind around it.
Precisely. But on a micro scale. And that altered airflow then encourages more of those bouncing grains to land right there on that growing bump.
Okay, I see.
The research also points out this interesting transition the grains experience moving from the hard surface where they bounce high onto the slightly softer rippled surface where they start to accumulate. That change in surface affects their bounce energy, making them more likely to deposit rather than just bounce away again.
So it's a feedback loop. Bump forms, changes wind, catches more sand, bump gets bigger.
Yes, exactly. It helps a proto-dune grow, feeding itself, much like larger dunes do. But the whole process is kicked off by this high bounce mechanism that wasn't really accounted for before on these types of surfaces.
So the big insight is, on hard or damp ground, sand doesn't just roll, it bounces high. And that high bounce is what lets these mini dunes get started so quickly when the sand finds a place to settle down.
That's the core idea, yes. And they took this further. Using this theory and all that detailed data they collected, Cothers, based in Paris, built a computer model.
A simulation to test the bouncing sand idea.
Right. And the model worked remarkably well. It managed to reproduce the formation of these mini dunes, their shapes, their rapid growth rates, just like they saw in the field studies in Namibia and other places.
Did the model only work for those dry Namibian conditions? Or
No, and that's a key strength. It also accurately simulated mini dune formation in the moist conditions they studied, I think in Colorado and Norfolk, UK.
so it works for both the hard, gravelly type surfaces and the damp beach sand type.
Exactly, which suggests this high bounce mechanism and the way the sand then accumulates is a more universal process for these small features than we previously thought. It's not just limited to one specific environment.
It gives us a much broader explanation then, not just for deserts.
Yes. And the model is also a tool, you know. Researchers can now use it to play around with the conditions.
Like what?
Well, you can change things like how much sand is flying around, how strong the wind is, and see how that affects whether the dunes form, how big they get, how quickly they change. It lets you explore different scenarios.
Makes sense. Run simulations. So what did the model show about, say, how they grow or disappear?
Pretty much what you'd intuitively expect, but it quantifies it. If you have strong winds constantly bringing in a good supply of that bouncing sand, the model shows the mini dunes will get bigger. More input equals growth.
Okay, straightforward.
But it also shows the reverse. If the wind drops, or the sand supply dwindles, or maybe the surface gets wet and stops the bouncing, the proto-dune doesn't just sit there, it starts to erode.
So they need that constant feed of bouncing sand to survive.
Very much so. They're dynamic. That explains why they can be so transient here 1 hour, gone the next. It depends entirely on that incoming flux of high-bouncing grains finding a place to stick.
Right, that connects back to them appearing and vanishing so quickly. Okay, this is fascinating for Earth. But you mentioned Mars earlier.
Yes. This is where it gets really exciting, potentially. The same research team, they're now taking this understanding.
The bouncing sand model.
Yeah, the whole mechanism. And they're applying it to look at features observed on the surface of Mars.
Seriously? Looking for mini dunes on Mars based on this?
Well, looking at small-scale sandy features on Mars, yes. Using images from orbiters and rovers, they want to see if similar features exist there. And if they do, could they have formed by a similar process? Sand bouncing higher in Mars's thin atmosphere and lower gravity, perhaps off harder rocky ground.
So trying to see if the physics works the same way, despite the huge differences between Earth and Mars.
Kind of.
Oh.
Or, what are the differences? How do Mars's unique conditions change how these things might form compared to Earth? It's using what we learned from, a beach ripple here to potentially interpret landscapes millions of miles away.
That's quite a leap. So let's bring it back. For you listening, why does understanding bouncing sand grains really matter?
Well, the main thing is it finally gives us a solid explanation for these really common features. Mini dunes on beaches, paths, riverbeds that the old theories couldn't properly handle. It shows sand movement is more complex than just simple rolling.
So next time you're out, maybe after a windy day, and you see those tiny sand ripples on the path or the shore, you can think, that might be the result of sand grains doing these surprisingly high bounces before finding a spot to settle. It's that dynamic process in action.
Exactly. And understanding how sand moves and accumulates on different surfaces isn't just, abstract geology. It's important for real-world stuff, like coastal erosion, how beaches change, or understanding dust and sand transport in arid regions, which relates to desertification. Environmental science needs this kind of detail. And now, obviously, planetary science, too, interpreting other worlds.
It is amazing, isn't it, how figuring out the precise way a tiny grain of sand bounces here on Earth can suddenly open up new ways of thinking about landscapes on Mars. It really connects the small scale, the everyday, to the extraterrestrial.
It absolutely does. It all came from looking really closely at something seemingly simple and realizing the existing explanation wasn't quite right.
Makes you wonder, doesn't it? What other common, maybe overlooked little phenomena right here on Earth might actually hold clues to much bigger scientific questions, maybe even about other planets, things hiding in plain sight.
That's a great thought to end on. There's probably a lot more out there like that.
Definitely something to think about. Well, thank you for joining us for this deep dive into the world of mini dunes.